Okay, so let's just imagine this. Here's us on the Earth, right? We're going to drop something. So let's say we have a ball. We're going to go ahead and drop that ball. Let's say we're going to drop it a meter above. So essentially what we're saying is, well, how do we find little g? I've already told you little g on Earth, right? We said it was 9.8. Well, how did we get that number? Okay, or how could we find that if we didn't do any experiments? All right, so we're just going to start with this. We'll start with FG. Up to today, what did I say the equation for FG was? mg, right? M times little g. Well, this is actually only true at the surface or close to the surface. This is not really the equation for FG anywhere else, only when you're close to the surface. Yeah?
Does that mean at sea level, does the altitude also?
Altitude matters, yeah. Now, as we'll see, it doesn't matter that much, but it is a factor. So if I want the true equation for Fg, I'm going to use Newton's equation. So this would be big G m over r squared. So if I'm close to the surface, I could use either equation. I have to use this. This works everywhere. mg only works when you're close to the surface. Okay? So if I wanted to find g at the surface, well, I could just say mg will be equal to this. Let's define our m's. When I say Fg equals mg, which m am I talking about? The mass of the ball or the mass of the Earth? The ball. And then what are these two masses? So notice what happens here. The mass of the ball cancels. So little g is not dependent on the ball's mass. And we learned that back on day 2 or day 3 of this class. When I drop things, its acceleration does not depend on the mass of the object, right? What does it depend on? The mass of the Earth. And then what does r mean here? So this is not 1 meter. This is not 1 meter, right? What is r defined as? Well, center to center. So this would be, we need to know the radius of the Earth. So this r value would actually be, truly speaking, I'll write this as r total. This r total would be the radius of the Earth plus the distance above the surface. Okay, the radius of the Earth plus the distance above the surface. Alright, so we need two values. What are those two values that we need to solve this? Okay, we need the mass of the Earth. What else? Radius of the Earth. So in your textbook, page 223, there's some useful planetary data. Okay, you'll be using this today and tomorrow. So we need the value for the mass and the radius of the Earth. So mass of the Earth, actually I'll write it here. Mass of the Earth is 5.98 times 10 to the 24th. The radius of the Earth, 6.38 times 10 to the 6th. Yes? No. So our total, so if I want to figure this out, notice what happens here. If I just expand this, I'm going to get 6,380,000. 6,380,000 meters plus 1. Okay, so what can we say is true about that 1 meter? It's negligible, right? It's insignificant. And in fact, to 3 digits, it doesn't even come into play at 3 digits. In fact, it doesn't really even come into play until you're like 4 or 5 digits, right? It won't even touch the third digit until you get to like 5,000 meters. So in this case, when you're at the surface, we might as well just say it's the radius of the Earth. Okay, now if you want, you could plug in that +1. Yes, you'll be a little bit accurate, but the 3 digits will all be the same. All right, so let's go ahead and find low g. So we're doing it for Earth. This would be the equation, though, for anywhere. If you did it on the moon, if you did it on Venus, you'd do the same thing. Okay, so go ahead and do it. I'll write it out. Again, the hardest part of this really is plugging it in. Make sure you can plug it in. Use the shortcuts that I showed you earlier. And you'll know that you did it right because the answer should look familiar to you.